Right now, as you're watching this, you're hurtling through space at over 67,000 miles per hour aboard a planet that orbits a star in a galaxy containing hundreds of billions of other stars. All part of a universe so vast that light from distant galaxies takes billions of years to reach your eyes. And yet, despite all our scientific achievements, despite our ability to peer into the hearts of atoms and capture images of black holes, we understand less than 5% of everything that exists. The other 95%, it's a complete mystery. Tonight, we're embarking on a journey into the deepest enigmas that have left the world's brightest minds scratching their heads in bewilderment. These aren't just gaps in our knowledge waiting to be filled. These are fundamental mysteries that challenge everything we thought we understood about reality itself. Welcome back to another exploration of the cosmos and its most perplexing secrets. Before we dive into these mind-bending mysteries together, I'd love to know where in the world you're tuning in from and what time it is in your corner of our cosmic neighborhood. And I'd be incredibly grateful if you gave this video a like and perhaps subscribe to join our growing community of cosmic truth seekers. Let's get going. The journey begins now. What I'm about to share with you will fundamentally change how you see the universe around you. By the time we're finished tonight, you'll understand why some of the most brilliant scientists in human history have called our cosmos stranger than we can suppose. You'll discover that the very fabric of reality is woven from threads we cannot see, guided by forces we cannot comprehend, and filled with phenomena that shouldn't exist according to our best theories. We're living in an age of unprecedented discovery, yet each new breakthrough seems to reveal 10 new mysteries for every question we answer. The James Webb Space Telescope is showing us galaxies that existed when the universe was barely a cosmic infant, yet they're so massive and mature they shouldn't be possible. Radio telescopes are detecting mysterious signals from deep space that appear and vanish without explanation. And everywhere we look, from the quantum realm to the cosmic web, we find evidence that our universe operates according to rules we're only beginning to glimpse. Chapter 1. The Invisible Universe, Dark Matter and Dark Energy. Let's begin with perhaps the most humbling discovery in the history of science. Everything you can see, touch and interact with in the entire observable universe, every star, planet, galaxy and nebula, every atom in your body, and every photon of light that has ever reached your eyes represents less than 5% of what actually exists. The other 95% is invisible. Scientists call this missing majority dark matter and dark energy, and their discovery has fundamentally rewritten our understanding of cosmic architecture. Dark matter makes up roughly 27% of the universe, while dark energy comprises a staggering 70%. Together they control the fate of everything that exists, yet we can neither see them nor directly detect them with any instrument we've ever built. The story of dark matter begins in the 1970s when astronomer Vera Rubin made an observation that shattered our cosmic worldview. She was studying how fast stars orbit around the centers of galaxies, expecting to find that stars on the outer edges move more slowly than those closer to the center, just like planets in our solar system. Instead, she discovered something impossible. The outer stars were moving just as fast as the inner ones, defying everything we understood about gravity and orbital mechanics. For these galaxies to hold together at such rotation speeds, there had to be far more matter present than we could see. The visible stars and gas clouds weren't nearly massive enough to generate the gravitational pull required. Something invisible was providing the missing mass, something that interacted gravitationally with ordinary matter but remained completely undetectable through electromagnetic radiation. This invisible scaffolding isn't just hiding in a few unusual galaxies. Computer simulations show that without dark matter, the cosmic web of galaxy clusters and superclusters that defines large-scale structure couldn't have formed at all. Dark matter appears to be the foundation upon which all visible cosmic architecture is built, like an invisible skeleton supporting the body of the universe. But what is this mysterious substance? Despite decades of sophisticated detection experiments, buried deep underground and sensitive enough to register the collision of a single theoretical particle, we still have no direct evidence of dark matter's true nature. Leading candidates include weakly interacting massive particles called WIMPs, hypothetical particles called axions, and sterile neutrinos that barely interact with ordinary matter. Each possibility opens doors to entirely new physics beyond our current understanding. If dark matter is mysterious, dark energy is absolutely mind-bending. This invisible force was discovered in the 1990s when astronomers studying distant supernovae made an observation that contradicted fundamental assumptions about cosmic evolution. Instead of finding that the universe's expansion was slowing down due to gravitational attraction between galaxies, they discovered that expansion is actually accelerating. Something is pushing space itself apart with ever-increasing strength, overcoming the gravitational pull of all matter in the universe. This force operates on scales so vast that its effects are invisible in our local cosmic neighborhood, but dominate the behavior of the universe as a whole. It's as if reality itself is being stretched by an invisible hand, driving galaxies apart at an ever-increasing rate. The implications are staggering. If dark energy continues to dominate cosmic evolution, the universe will eventually enter a phase called the Big Rip, where the accelerating expansion becomes so extreme that it overcomes all fundamental forces. First, galaxy clusters will be torn apart, then individual galaxies, then solar systems, then planets, then atoms themselves. The universe would end not in fire or ice, but in the complete dissolution of all structure and organization. Yet we have absolutely no idea what dark energy actually is. Some theories suggest it's a property of space itself, that empty vacuum contains inherent energy that drives expansion. Others propose it's a dynamic field that evolves over cosmic time, potentially changing its behavior in ways we can't predict. The most disturbing possibility is that our understanding of gravity itself is fundamentally wrong, and the phenomena we attribute to dark energy result from modifications to Einstein's theories that we haven't yet discovered. Chapter 2: Messages from the Void, Fast Radio Bursts. Deep in the cosmos, something is sending us messages we don't understand. These signals appear without warning, blast across space with the energy of hundreds of millions of suns, and vanish in milliseconds, leaving behind only radio echoes and baffled astronomers. They're called fast radio bursts, or FRBs, and they represent one of the most perplexing phenomena in modern astronomy. First discovered in 2007 when astronomer Duncan Lorimer was analysing archival data from the Parkes radio telescope, these mysterious signals have challenged every attempt to explain their origin and nature. Picture this. Somewhere in the distant universe, an event occurs that releases more energy in a few milliseconds than our sun produces in an entire day. This energy is concentrated in radio wavelengths and beamed across billions of light-years of space with pinpoint precision. The burst is so brief that if you blinked, you'd miss it, yet so powerful that it can be detected by radio telescopes across the globe. What makes fast radio bursts so mysterious isn't just their incredible energy output, but their bizarre characteristics. Most appear to be one-time events, flashing once and never repeating. Others, however, follow strange patterns, repeating at seemingly random intervals or in sequences that suggest some form of underlying structure or intelligence. The first repeating FRB, designated FRB 121102, has produced hundreds of bursts since its discovery, each one slightly different from the last. Some appear to follow a 157-day cycle, active for 90 days then silent for 67 days, suggesting an orbital mechanism or some form of periodic activity. Others show sudden changes in their emission properties, as if the source itself is evolving or being affected by its environment. Even more puzzling is the distribution of these signals across the sky. FRBs appear to come from random directions throughout the universe, with no obvious correlation to known astronomical objects or structures. Some originate from within our own galaxy, while others travel across billions of light years from the most distant reaches of the observable universe. The leading theories for FRB origins read like science fiction. Some astronomers propose they're caused by highly magnetized neutron stars, called magnetars, whose magnetic fields are so intense they can tear apart atomic nuclei. Others suggest they result from the collision of neutron stars or the evaporation of primordial black holes. More exotic possibilities include cosmic strings vibrating through spacetime or even techno-signatures from advanced alien civilizations. Recent discoveries have only deepened the mystery. In 2020, astronomers detected an FRB originating from within our own galaxy, allowing for the first time detailed study of the source environment. The burst came from a magnetar called SGR 1935 and 2154, providing the first direct link between FRBs and these exotic stellar remnants. However, this magnetar-produced FRB was thousands of times weaker than typical extragalactic bursts, suggesting that either galactic and extragalactic FRBs have different origins, or the mechanisms involved are far more complex than we imagined. Perhaps most intriguingly, some FRBs show signs of artificial structure. Their signals appear to be dispersed in ways that suggest they've passed through multiple, distinct regions of ionized gas, creating patterns that some researchers argue are too organized to be natural. While the scientific consensus firmly rejects the idea that FRBs represent alien communications, the possibility continues to fuel speculation and drive more sophisticated analysis of their properties. The James Webb Space Telescope and next-generation radio arrays are beginning to provide unprecedented detail about FRB environments and characteristics. Each new observation adds pieces to the puzzle, but the complete picture remains frustratingly out of reach. We're detecting these cosmic screams from across the universe, yet we still can't definitively explain what's causing them or why they exist. Chapter 3. The Greatest Question: Why anything exists at all. Perhaps no mystery is more fundamental than this simple question. Why is there something rather than nothing? According to our best understanding of physics, the universe should never have existed in the first place. This isn't philosophical speculation. It's a concrete problem rooted in the fundamental laws of particle physics. When matter and antimatter meet, they annihilate each other completely, converting their mass into pure energy according to Einstein's famous equation, E equals mc squared. In the early universe, immediately after the Big Bang, equal amounts of matter and antimatter should have been created. These particles should have found each other, annihilated completely, and left behind a universe containing nothing but photons and empty space. Yet here we are, surrounded by matter, composed of matter, living on a planet made of matter, orbiting a star made of matter, in a galaxy filled with billions of other matter-based stars. The very fact that you exist to contemplate this mystery represents a violation of what our theories predict should have happened. This conundrum is known as the matter-antimatter asymmetry problem, and it suggests that the early universe contained a subtle but crucial imbalance. For every billion antimatter particles created in the cosmic furnace of the Big Bang, there were approximately 1,000,000,001 matter particles. This tiny excess, a difference of just one part in a billion, allowed matter to survive the Great Annihilation and become the foundation for everything we observe. But why did this asymmetry exist? What process in the early universe could have created such a precise imbalance? The answer involves some of the most exotic physics imaginable, touching on concepts that push the boundaries of human understanding. One possibility lies in the behavior of particles called baryons during the first fraction of a second after the Big Bang. According to a set of conditions known as the Sakharov criteria, 3 requirements must be met for matter to triumph over antimatter: baryon number violation, charge and parity violation, and thermal non-equilibrium. While we've observed hints of these processes in particle accelerators, the mechanisms remain poorly understood and insufficient to explain the observed matter dominance. Another theory involves hypothetical particles called axions, which could have influenced the matter-antimatter balance through their interactions with other fundamental fields. These particles, if they exist, would be so weakly interacting that they've escaped detection despite decades of searching. Their properties could explain not only the matter asymmetry, but also contribute to dark matter, solving 2 cosmic mysteries simultaneously. Even more speculative theories suggest that the asymmetry results from processes involving extra dimensions of space, cosmic inflation, or the decay of exotic particles that existed only in the universe's first moments. Some models propose that antimatter wasn't destroyed but instead exists in parallel regions of spacetime that we cannot access or observe. The implications of solving this mystery extend far beyond academic curiosity. Understanding why matter dominates over antimatter would provide crucial insights into the fundamental nature of reality itself. It would tell us whether our existence is the result of precise fine-tuning, random cosmic luck, or deeper physical principles we haven't yet discovered. Recent experiments at the Large Hadron Collider and other particle accelerators are probing the subtle differences between matter and antimatter with unprecedented precision. Scientists are studying particles called mesons that oscillate between matter and antimatter states, searching for tiny violations of fundamental symmetries that might explain cosmic evolution. Meanwhile, astronomical observations are pushing the boundaries of how far back in time we can observe, seeking direct evidence of the processes that shaped the early universe. The James Webb Space Telescope is revealing galaxies that formed when the universe was less than 5% of its current age, providing windows into epochs when the matter-antimatter balance was still being established. Chapter 4: The Great Silence. Where are the aliens? In 1950, during a casual lunch conversation at Los Alamos National Laboratory, physicist Enrico Fermi posed a question that has haunted humanity ever since. Where is everybody? He was referring to the apparent absence of extraterrestrial civilizations despite the vast number of potentially habitable worlds in our galaxy. This simple question contains within it one of the most profound mysteries in all of science. The mathematics seem overwhelming in favor of alien life. Our galaxy contains roughly 400 billion stars, many similar to our Sun. Recent discoveries by space telescopes suggest that rocky planets in habitable zones are common, with potentially billions of Earth-like worlds in the Milky Way alone. Some of these planets orbit stars that are billions of years older than our Sun, providing ample time for life to evolve and develop advanced technology. Yet despite decades of searching with increasingly sophisticated instruments, we have found absolutely no evidence of extraterrestrial intelligence. No radio signals, no megastructures harvesting stellar energy, no obvious signs of galactic engineering projects that advanced civilizations would inevitably undertake. The cosmos appears eerily silent. This contradiction between expectation and observation is known as the Fermi Paradox, and its implications is common in the universe as are both fascinating and terrifying. If life our understanding of biology and planetary science suggests, then where are all the aliens? Several categories of solutions have been proposed, each with disturbing implications for humanity's future. The first possibility is that we're alone, that Earth represents an extraordinary cosmic accident where life emerged against overwhelming odds. This would make us unimaginably precious, the only known instance of matter organizing itself into consciousness and contemplating its own existence. The second possibility is that life is common, but intelligence is rare. Perhaps the evolution of complex brains capable of technology and abstract reasoning requires such specific conditions and unlikely evolutionary pathways that it occurs only once per galaxy, or even less frequently. We might be surrounded by worlds teeming with microbial life, but devoid of beings capable of building radio telescopes or spacecraft. The third, and most unsettling possibility, is that intelligent life regularly evolves, but consistently destroys itself before achieving interstellar communication or travel. This scenario, sometimes called the Great Filter, suggests that technological civilizations face universal challenges that prove insurmountable. Nuclear war, environmental collapse, artificial intelligence gone wrong, or other catastrophes might represent inevitable bottlenecks that prevent species from surviving their technological adolescence. Recent developments in our search for extraterrestrial intelligence have added new dimensions to the mystery. The discovery of potentially habitable exoplanets has accelerated dramatically, with thousands of confirmed worlds and many showing signs of atmospheric water vapor or other biosignatures. Yet these discoveries have only highlighted the absence of obvious technological signatures. Some researchers have proposed that we're looking in the wrong places or for the wrong signals. Advanced civilizations might communicate using technologies we haven't invented, operate on timescales that make detection difficult, or deliberately remain hidden to avoid attracting attention from potentially hostile neighbors. The dark forest hypothesis suggests that the galaxy might be filled with civilizations that have learned to stay silent, knowing that revealing their location could attract destructive attention. Another possibility is that we're living in a universe where intelligence naturally turns inward rather than expanding outward. Advanced civilizations might discover that virtual reality, nanotechnology, or other technologies provide more rewarding experiences than costly and dangerous interstellar expansion. They might exist in computational substrates we can't detect, having uploaded their consciousness into digital realms that offer unlimited possibilities without the constraints of physical space travel. The search continues with ever more sophisticated methods. Projects like Breakthrough Listen are scanning millions of stars for artificial radio signals, while others look for optical flashes or infrared signatures of massive engineering projects. The James Webb Space Telescope is beginning to analyze exoplanet atmospheres for potential biosignatures, searching for combinations of gases that might indicate biological activity. Perhaps most intriguingly, some researchers are investigating whether evidence of past visitation might exist in our own solar system. Ancient artifacts on the Moon, asteroids, or even Earth itself could preserve signs of extraterrestrial technology across geological timescales. While no convincing evidence has been found, the systematic search has barely begun. The Fermi Paradox forces us to confront uncomfortable questions about our own future. Are we approaching challenges that have stopped every other civilization that has ever existed? Or are we on the verge of joining a galactic community that has simply been waiting for us to develop the wisdom and technology necessary for contact? The answer to Fermi's question will determine not just our understanding of life in the universe, but our perception of our own cosmic significance and the challenges that lie ahead for human civilization. Chapter 5. The Impossible Galaxies, What James Webb is Showing Us. Just when we thought we were beginning to understand cosmic evolution, the James Webb Space Telescope opened its golden eye and shattered our most fundamental assumptions about how the universe grew from simplicity to complexity. What Webb is revealing in the deepest reaches of space should be impossible, according to our best models of cosmology. The telescope is detecting fully formed, massive galaxies existing when the universe was barely 400 million years old, less than 3% of its current age. These aren't the small primitive star clusters we expected to find in the cosmic dawn. They're sophisticated galactic structures containing billions of stars, some already showing signs of heavy element enrichment that should have taken billions of years to develop. Picture trying to find a fully grown oak tree in a forest that was planted last week. That's essentially what we're observing in the early universe. These ancient galaxies are so massive and mature that they challenge our understanding of how structure formation works on cosmic scales. The problem isn't just their size, but the speed at which they must have assembled. According to our models, the first stars shouldn't have formed until at least 100 million years after the Big Bang, and these primordial stars should have been fundamentally different from modern ones. They should have been massive, short-lived, and composed entirely of hydrogen and helium, since no heavier elements existed yet. These first-generation stars, called population Thoride stars, were supposed to live fast and die young, exploding as supernova and seeding space with the heavy elements necessary for second-generation star formation. Only, after several cycles of stellar birth, death, and element dispersal, should complex galactic structures have been possible. Yet Webb is finding galaxies that appear to have skipped this gradual build-up entirely. Some show spectroscopic evidence of oxygen, carbon, and other heavy elements in concentrations that should have required billions of years of stellar processing. Others contain supermassive black holes that are actively feeding and growing, despite existing in an era when such objects shouldn't have had time to form. One particularly puzzling discovery involves galaxies that appear surprisingly red in Webb's infrared observations. This redness could indicate either that these galaxies are older and more evolved than expected, or that they contain unusual dust compositions that alter their light in ways we don't understand. Either explanation requires revising our models of early cosmic evolution. The mystery deepens when we consider the cosmic microwave background radiation, which provides a detailed snapshot of the universe when it was only 380,000 years old. This ancient light shows a remarkably smooth and uniform cosmos, with only tiny density fluctuations that served as seeds for later structure formation. The amplitude of these fluctuations seems far too small to have grown into the massive galaxies Webb is now detecting. Some astronomers are proposing radical solutions to this paradox. Perhaps dark matter behaves differently in the early universe than our models assume, allowing structures to collapse and form stars much more rapidly than we thought possible. Others suggest that the first supermassive black holes formed through exotic processes that bypass the normal stellar evolution pathway, growing directly from primordial density fluctuations or the collapse of dark matter structures. Even more speculative theories propose that these early galaxies formed around primordial black holes left over from cosmic inflation, or that they represent evidence of alternative cosmological models where the universe underwent multiple phases of expansion and contraction before settling into its current evolutionary path. The implications extend far beyond academic cosmology. If galaxies could form so quickly in the early universe, it suggests that the conditions for complex chemistry and potentially even life might have existed much earlier than we previously imagined. The heavy elements necessary for rocky planet formation and biological processes could have been distributed throughout space when the universe was still in its infancy. Chapter 6. The Cosmic Voids. Emptiness that shouldn't exist. Imagine a region of space so empty that if our solar system were placed at its centre, the nearest star would be hundreds of millions of light years away. These vast bubbles of nothingness, called cosmic voids, represent some of the largest and most mysterious structures in the universe. At first glance, empty space might not seem mysterious. After all, most of the universe consists of vacuum punctuated by occasional atoms and particles. But cosmic voids are different. They're not just empty, they're impossibly empty, containing less than 1/10 the average density of matter found elsewhere in the cosmos. The largest known void, called the Boötes void, or the Great Nothing, spans roughly 330 million light-years across. If you lived in a galaxy at its centre, you would see virtually no other galaxies in any direction, creating a view of the cosmos so barren it would fundamentally alter your understanding of cosmic architecture. The night sky would appear almost completely black, devoid of the distant galactic light that provides the faint background glow we observe from Earth. What makes these voids truly mysterious isn't just their size, but their very existence. According to our understanding of cosmic evolution, matter should be distributed more uniformly throughout space. While gravity naturally creates clumps and concentrations over time, it shouldn't be able to evacuate such enormous regions so completely. The Cosmic Web model describes how dark matter forms filaments and nodes where galaxies cluster, connected by vast networks of matter streams. But this model struggles to explain how such enormous voids could form and maintain their emptiness over billions of years. Gravitational forces should have drawn at least some matter into these regions, yet they remain stubbornly vacant. Recent surveys have revealed that these voids aren't completely empty, but contain a sparse population of extremely isolated galaxies. These void galaxies are among the loneliest objects in the universe, separated from their nearest neighbours by distances that dwarf the spaces between galaxy clusters. They appear to have evolved in almost complete isolation, creating unique laboratories for studying galactic development without environmental influences. Some of these void galaxies show unusual properties that hint at exotic physics. They often appear younger and less evolved than galaxies of similar mass in denser regions, as if their isolation has somehow slowed their development. Others show signs of active star formation that should have ceased long ago given their apparent age and mass. The mystery deepens when we consider how voids affect the cosmic microwave background radiation. Light passing through these enormous empty regions experiences a phenomenon called the integrated Sachs-Wolf effect, where the expansion of space itself alters the photon's energy. This creates cold spots in the microwave background that correspond to void locations. But the observed temperature differences are larger than theoretical models predict. Some astronomers have proposed that voids might be expanding faster than the general cosmic expansion, actively growing and evacuating matter through unknown processes. This could indicate modifications to general relativity on the largest scales, or the influence of dark energy that behaves differently in low-density environments. Other theories suggest that voids formed through primordial processes in the early universe, possibly related to cosmic inflation or phase transitions in fundamental fields. These models propose that certain regions experience different expansion rates or particle physics during the universe's first moments, creating seeds that eventually grew into today's cosmic voids. Perhaps most intriguingly, some researchers have suggested that voids might provide windows into extra dimensions or alternative theories of gravity. The modified gravitational behaviour in these low-density regions could reveal deviations from Einstein's general relativity that are masked in denser environments where matter dominates space-time curvature. Chapter 7. The Quantum Consciousness Enigma. Deep within your brain, roughly 86 billion neurons are firing in patterns so complex they create the phenomenon you experience as consciousness. Yet despite decades of neuroscientific research and philosophical inquiry, we have absolutely no idea how this happens. The mystery of consciousness represents perhaps the deepest chasm between our scientific understanding and our direct experience of reality. We can map every neural pathway, measure every electrochemical signal, and predict many aspects of brain behavior with remarkable precision. But we cannot explain why any of this neural activity should be accompanied by the inner, subjective experience of being you. This isn't simply a gap in our knowledge that will eventually be filled by more sophisticated neuroscience. It's what philosophers call the hard problem of consciousness, the seemingly unbridgeable explanatory gap between objective physical processes and subjective mental experience. Consider the redness you experience when looking at a rose, the taste of chocolate on your tongue, or the feeling of sadness when remembering a lost friend. These qualia, as philosophers term them, have no obvious relationship to the neural firing patterns that correlate with them. Why should electrical signals in your visual cortex create the specific experience of redness rather than blueness, or no conscious experience at all? The problem becomes even more perplexing when we consider that consciousness appears to violate fundamental principles of physics. According to our best scientific theories, the universe consists of particles and fields interacting according to mathematical laws. There's no place in this framework for subjective experience, yet consciousness is the one aspect of reality we know with absolute certainty exists. Some neuroscientists propose that consciousness emerges from the complex interactions of neural networks, much like wetness emerges from H2O molecules. But this analogy breaks down when examined closely. Wetness is simply a description of how water molecules behave in bulk. There's no additional property that needs explaining. Consciousness, however, involves something genuinely new, the felt experience of what it's like to be aware. Recent theories have attempted to bridge this explanatory gap through increasingly exotic proposals. Integrated information. Theory suggests that consciousness corresponds to integrated information processing in physical systems, with different arrangements of matter supporting different levels of conscious experience. This theory implies that consciousness might exist throughout the natural world, from simple particles to complex computers. Even more radical is the possibility that consciousness represents a fundamental feature of reality, like mass or electric charge, rather than an emergent property of complex systems. Panpsychist theories propose that all matter possesses some form of primitive consciousness, which combines and integrates in human brains to create our unified conscious experience. Quantum theories of consciousness suggest that quantum mechanical processes in neural microtubules might create the conditions necessary for conscious experience. These models propose that consciousness arises from quantum coherence and entanglement effects that operate at scales previously thought impossible in the warm, noisy environment of biological systems. The implications extend far beyond neuroscience into fundamental questions about the nature of reality itself. If consciousness cannot be reduced to purely physical processes, it suggests that our materialist worldview is fundamentally incomplete. We might need entirely new categories of scientific explanation that incorporate subjective experience as a basic feature of the universe. This mystery also raises profound questions about artificial intelligence and machine consciousness. As our computers become increasingly sophisticated, will they spontaneously develop inner experience, or will they remain elaborate but unconscious information processors? The answer depends on whether consciousness requires specific biological processes or can emerge from any sufficiently complex information processing system. The search for consciousness in the brain has led to remarkable discoveries about neural correlates of awareness, the specific brain states that correspond to different conscious experiences. But identifying correlations is different from explaining causation. We can predict when someone will be conscious and what they might experience, but we still cannot explain why there should be any experience at all. Perhaps most mysteriously, consciousness appears to have genuine causal power in the physical world. Your decision to raise your hand somehow translates into actual hand movement, suggesting that subjective mental states can influence objective physical processes. This mind-matter interaction challenges our understanding of causation and suggests that consciousness might play a fundamental role in the operation of physical reality itself. Chapter 8: The Multiverse Mystery: Infinite Realities Beyond Our Own. What if everything you've ever known, every galaxy we can observe, every particle we can detect, represents just one tiny bubble in an infinite ocean of parallel universes? This possibility, once relegated to science fiction, has emerged as a serious scientific hypothesis supported by some of our most successful theories in physics. The multiverse concept arises naturally from several independent lines of theoretical development, each suggesting that our observable universe might be just one member of an unimaginably vast ensemble of cosmic regions with different physical properties, histories, and even fundamental laws. The most direct path to the multiverse comes from cosmic inflation, the theory that explains how our universe expanded exponentially in its first fraction of a second. If inflation occurred in our cosmic neighborhood, it likely occurred elsewhere as well, creating countless other bubble universes separated by vast regions of still inflating space. Each bubble would begin with different initial conditions and potentially different physical constants, creating a diverse landscape of possible realities. In some of these parallel universes, the fundamental forces might be stronger or weaker than in ours. The mass of the electron could be different, the speed of light might vary, or gravity could operate according to alternative mathematical relationships. Most of these universes would be sterile, unable to form stars, planets, or complex structures. But in rare cases, the physical constants might align to create worlds even more hospitable to complexity and life than our own. Quantum mechanics provides another pathway to infinite parallel realities through the many worlds interpretation. Every quantum measurement that appears to have a random outcome might actually split reality into multiple branches, with each possible result occurring in a different parallel universe. This means that every quantum event throughout cosmic history has created an exponentially branching tree of alternative realities. In one nearby parallel universe, you might have chosen a different career path. In another, dinosaurs might never have gone extinct. In still others, fundamental historical events unfolded differently, creating worlds with alternative technologies, societies, and evolutionary pathways. The total number of these quantum branches would be literally infinite, encompassing every possible variation of cosmic history. String theory, our most ambitious attempt to unify quantum mechanics with general relativity, suggests yet another form of multiverse. The mathematical landscape of string theory contains roughly 10 to the power of 500 possible solutions, each corresponding to a different set of physical laws and particle properties. If all these solutions are realized somewhere in a vast cosmic ensemble, our universe would be just one point in an unimaginably large space of possibilities. The evidence for multiverse theories remains indirect but compelling. The apparent fine-tuning of physical constants in our universe becomes less mysterious if countless other universes exist with different constants. We naturally find ourselves in a universe compatible with our existence, not because it was designed for us, but because we could only evolve in such a universe regardless of how many sterile alternatives exist. Recent observations of the cosmic microwave background radiation have revealed subtle anomalies that some researchers interpret as evidence of collisions between our universe and neighbouring bubble universes during the inflationary epoch. These cosmic bruises would represent the most direct observational evidence for the multiverse, though alternative explanations remain possible. The philosophical implications of infinite parallel realities are staggering. If the multiverse contains every possible variation of cosmic history, then every possible version of your life exists somewhere in the vast ensemble. There are universes where you made different choices, where historical events unfolded alternatively, where the laws of physics permit entirely different forms of existence. This raises profound questions about identity, free will, and moral responsibility. If every possible action you might take occurs in some parallel reality, what meaning can we attach to the choices we make in this particular universe? Are we responsible for decisions that our parallel selves make differently in other realities? The multiverse also challenges our understanding of probability and scientific prediction. If all possible outcomes occur somewhere in the infinite ensemble, how can we make meaningful statements about what's likely to happen in our particular branch of reality? Some physicists argue that this leads to a complete breakdown of scientific predictability, while others propose new frameworks for reasoning about probabilities in infinite universes. Perhaps most unsettling is the possibility that we might not be living in a typical universe at all. If conscious observers are rare throughout the multiverse, we might find ourselves in one of the unusual realities where observation and measurement are possible. This observer selection effect could bias our understanding of fundamental physics in ways we haven't yet recognized. The search for multiverse evidence continues through increasingly sophisticated cosmological observations and theoretical developments. Projects studying the cosmic microwave background, dark energy, and quantum foundations all probe aspects of reality that might reveal signs of parallel universes or alternative cosmic domains. Whether the multiverse represents objective reality or merely a mathematical curiosity remains one of the most profound open questions in modern science. The answer will determine not just our understanding of cosmology, but our entire conception of existence, probability, and our place in the vast landscape of possible realities. But perhaps the most haunting aspect of the multiverse mystery is this: if infinite parallel realities exist, containing every possible variation of cosmic history, then somewhere in that vast ensemble of possibilities, there are versions of you reading these very words with subtly different thoughts, in worlds with slightly different physics, under stars that shine with alternative light. The question isn't whether these parallel selves exist, but whether you'll ever find a way to reach across the infinite barriers that separate one reality from another, to touch the hand of possibility itself and discover what truths lie hidden in the spaces between worlds. Chapter 9. The Time Problem. Why does the universe remember? Time might be the most familiar aspect of your existence, yet it harbours mysteries that strike at the very foundation of physical reality. Every second that ticks by on your clock represents one of the deepest, unsolved puzzles in all of science. Why does time have a direction? This isn't a philosophical question about the nature of temporal experience. It's a concrete problem rooted in the fundamental laws of physics. Nearly every equation that governs the behaviour of matter and energy works equally well, whether time flows forward or backward. The laws of thermodynamics, quantum mechanics, and even general relativity contain no inherent preference for temporal direction. Yet the universe around us is filled with irreversible processes that create what we experience as the arrow of time. Consider the simple act of dropping a coffee cup. The cup falls, shatters against the floor, and releases heat and sound energy into the room. You've never seen the reverse process occur spontaneously, heat and sound converging from the room to reassemble a broken cup that then leaps upward into your hand. Both scenarios are equally compatible with the fundamental laws of physics, yet only one ever occurs in our universe. This temporal asymmetry becomes even more mysterious when we examine it at the quantum level. Individual particle interactions show no preferred temporal direction. An electron absorbing a photon looks identical to the time-reverse process of an electron emitting a photon. Yet when billions of these reversible interactions combine, they somehow create the irreversible macroscopic world we inhabit. The standard explanation involves entropy, the measure of disorder in physical systems. The second law of thermodynamics states that entropy always increases over time, creating the thermodynamic arrow that defines temporal direction. But this explanation merely pushes the mystery deeper. Why did the universe begin in such an extraordinarily low entropy state that entropy could increase for billions of years? The early universe, immediately after the Big Bang, existed in a condition of remarkable order and uniformity. The cosmic microwave background radiation shows temperature variations of only 1 part in 100,000, representing an almost impossibly organized initial state. This primordial order provided the entropy gradient that has been driving cosmic evolution ever since. Yet explaining why the universe began in such an ordered state requires invoking processes we don't understand. Some theories propose that cosmic inflation naturally created low entropy initial conditions, but inflation itself requires fine-tuned parameters that seem to push the mystery back another level. Other models suggest that our universe emerged from quantum fluctuations in a pre-existing vacuum, but this merely shifts the question to why that vacuum possessed the specific properties necessary for universe creation. Even more puzzling is the relationship between time and consciousness. Your subjective experience of temporal flow, the sense that moments pass from future through present into past, has no obvious counterpart in physical theories. Physics describes correlations between different spatial and temporal coordinates, but it contains no mechanism that could create the flowing, experiential quality of time that defines conscious awareness. Recent experiments in quantum mechanics have revealed additional temporal mysteries that challenge our understanding of causality itself. Quantum entanglement appears to operate instantaneously across any distance, suggesting that the temporal relationship between cause and effect might be more complex than classical physics assumes. Some interpretations of quantum mechanics propose that future measurements can influence past quantum states, creating causal loops that violate our intuitive understanding of temporal order. The mystery deepens when we consider the relationship between time and information. Every physical process involves the transformation and flow of information through space and time. But information theory suggests that the total amount of information in the universe should remain constant. Yet we observe continuous creation of new information through quantum measurements, biological evolution, and conscious observation. Chapter 10. The Vacuum Catastrophe. The Energy of Empty Space. What you think of as empty space, the vacuum that exists between atoms and stars, might contain enough energy to destroy the universe trillions of times over. This isn't science fiction speculation. It's one of the most precise and disturbing predictions of modern physics. According to quantum field theory, empty space isn't actually empty. It seethes with virtual particles that pop into existence and annihilate each other in timeframes so brief they escape direct detection. These quantum fluctuations should contribute to the energy density of vacuum itself, creating what physicists call zero-point energy. The problem emerges when you try to calculate how much energy these fluctuations should produce. Using the standard methods of quantum field theory, the energy density of empty space comes out to be roughly 10 to the power of 120 times larger than what we observe through cosmic expansion. This represents the worst theoretical prediction in the history of science, a discrepancy so enormous it defies comprehension. To put this number in perspective, imagine trying to predict the height of a person and getting an answer of 10 to the power of 120 meters, a distance that dwarfs not just our solar system, but the entire observable universe. That's the level of disagreement between theory and observation when we try to understand vacuum energy. This vacuum catastrophe, as physicists call it, reveals fundamental gaps in our understanding of quantum mechanics, general relativity, and the nature of space itself. If quantum fluctuations really did contribute to vacuum energy at the predicted levels, space would be so curved by this enormous energy density that atoms couldn't exist, let alone stars, planets, or conscious beings. Yet somehow, the actual vacuum energy density is almost exactly zero. Not precisely zero, because we know that dark energy exists and contributes a small but measurable energy to empty space. But the observed value is so minuscule compared to theoretical predictions that it suggests either our calculations are fundamentally wrong, or some unknown mechanism is cancelling out the quantum contributions with extraordinary precision. Various solutions have been proposed, each more exotic than the last. Supersymmetry theories suggest that every known particle has a corresponding superpartner with opposite contributions to vacuum energy, creating perfect cancellation. But supersymmetric particles have never been detected, despite decades of searching, and the energy scales required for such cancellation seem incompatible with other aspects of particle physics. Other theories propose that the vacuum energy calculation is simply wrong, that quantum field theory breaks down when applied to the energy of empty space itself. This could indicate the need for entirely new approaches to quantum mechanics that avoid the vacuum catastrophe while preserving the theory's remarkable successes in describing particle interactions. Perhaps most intriguingly, some physicists have suggested that the vacuum catastrophe reveals fundamental limits to the precision of physical predictions. If the universe operates according to discrete, granular principles at the smallest scales, then our continuous, mathematical descriptions might be approximations that break down when pushed to their logical extremes. The anthropic principle offers another perspective on this mystery. If most possible universes have vacuum energies that prevent structure formation, then we naturally find ourselves in one of the rare realities where vacuum energy is small enough for complexity to emerge. This explanation requires accepting the existence of multiple universes with different physical properties, a multiverse where our apparently fine-tuned vacuum represents just one possibility among countless others. Recent developments in string theory and quantum gravity have provided new approaches to the vacuum catastrophe, but no definitive solutions. Some string models suggest that extra dimensions of space might provide mechanisms for vacuum energy cancellation, while others propose that the observed vacuum energy represents a dynamical quantity that evolves over cosmic time. Chapter 11: The Horizon Problem. Why is everything the same temperature? When you look up at the night sky, you're observing one of the most perfect examples of cosmic uniformity ever discovered. The cosmic microwave background radiation, the afterglow of the Big Bang, maintains the same temperature in every direction to within 1 part in 100,000. This remarkable uniformity represents one of the most puzzling aspects of our universe's structure. The mystery lies in the fact that widely separated regions of the cosmic microwave background should never have been in contact with each other. Light travelling at the cosmic speed limit simply hasn't had enough time since the Big Bang to carry information between these distant regions, yet somehow they all reached exactly the same temperature. Imagine heating a large metal bar by placing torches at opposite ends. The middle section would remain cool because heat takes time to flow from the hot ends toward the centre. For the entire bar to reach uniform temperature, you would need to wait for thermal equilibration to occur through direct contact between neighbouring regions. The cosmic microwave background presents the same puzzle on a universal scale. Regions of space separated by distances that light couldn't have traversed in the age of the universe somehow achieved thermal equilibrium. This is known as the horizon problem, and it suggests either that our understanding of cosmic expansion is wrong, or that some unknown process created this uniformity. The leading solution involves cosmic inflation, a brief period of exponential expansion that occurred in the universe's first fraction of a second. During inflation, regions that were initially in thermal contact became stretched to cosmic scales, carrying their equilibrated temperature with them. This would explain why widely separated parts of the cosmic microwave background show identical temperatures. They were once close neighbours that got pulled apart by inflating space. But inflation itself raises new mysteries. What caused this period of accelerated expansion? Why did it start and stop at precisely the right times? The mechanism requires a scalar field called the inflaton that behaves in very specific ways, rolling down a potential energy curve with parameters that seem fine-tuned for successful universe creation. Recent observations have revealed subtle variations in the cosmic microwave background that provide clues about inflation's properties. These tiny temperature fluctuations represent quantum fluctuations that got stretched to cosmic scales during inflation, seeding the density variations that eventually grew into galaxies and galaxy clusters. The patterns match inflation predictions remarkably well, providing strong evidence for this exotic phase of cosmic evolution. Yet alternative theories continue to challenge the inflation paradigm. Some models propose that the universe underwent a phase of contraction before the Big Bang, during which thermal equilibration could have occurred. Others suggest that the horizon problem reflects fundamental misunderstandings about the nature of time and causality in the early universe. The horizon problem also connects to deeper questions about the nature of physical laws themselves. If inflation is correct, then the observable universe represents just a tiny fraction of a much larger cosmic domain that underwent similar expansion. Different regions of this extended universe might have evolved with different physical constants, or even different fundamental forces. Chapter 12. The Lithium Problem. Missing elements from the Big Bang. In the first few minutes after the Big Bang, when the universe was hot enough for nuclear fusion, but cool enough for atomic nuclei to survive, a cosmic alchemy session created the lightest elements in the periodic table. This process, called Big Bang nuclear synthesis, should have produced specific ratios of hydrogen, helium, and lithium that we can calculate with remarkable precision. The predictions match observations beautifully for hydrogen and helium. Roughly 75% of ordinary matter consists of hydrogen, while helium makes up most of the remainder, exactly as the theory predicts. These elements formed during a narrow window when the universe's temperature and density were perfect for nuclear fusion, creating one of the most successful quantitative predictions in all of cosmology. But lithium presents a glaring problem. Observations of the oldest stars in our galaxy show lithium abundances that are roughly 3 times lower than Big Bang nuclear synthesis predicts. This might seem like a minor discrepancy, but it represents a fundamental breakdown in our understanding of the universe's first few minutes. The missing lithium can't be explained by stellar processing, because the oldest stars should preserve the primordial abundances created during nuclear synthesis. These ancient stars form from gas clouds that hadn't yet been contaminated by heavy elements from later generations of stars. Their surface compositions should provide direct windows into the chemical composition established during the Big Bang. Various solutions have been proposed, each with disturbing implications for our understanding of fundamental physics. Perhaps the oldest stars have destroyed their surface lithium through convective mixing that brings the element into hot stellar interiors, where it gets burned into heavier elements. But detailed stellar models struggle to explain how such mixing could occur efficiently enough to reduce lithium abundances by the observed factor. Other theories suggest that the nuclear reaction rates during Big Bang nuclear synthesis were different from laboratory measurements. If the reactions that create lithium proceeded more slowly in the early universe, or if additional processes destroyed lithium after its creation, the observed abundances might be explained. But such modifications would require new. Perhaps most intriguingly, the lithium problem may hint at physics beyond the standard model. suggesting the early universe contained exotic particles or fields that shaped nucleosynthesis. Hypothetical particles, like axions, sterile neutrinos, or dark matter candidates, could have altered expansion rates or nuclear interactions during the crucial epoch. Some researchers have proposed that the lithium disco synthesis hypercrepancy provides evidence for time-varying fundamental constants. If the strength of nuclear forces or the masses of elementary particles were different during Big Bang nucleosynthesis, the predicted element abundances would change accordingly. While such variations would require revolutionary modifications to physics, they might explain not just the lithium problem, but other cosmological puzzles as well. The mystery has taken on new urgency with recent observations from the James Webb Space Telescope, which is beginning to measure element abundances in some of the most distant and oldest galaxies ever observed. These measurements could provide independent tests of Big Bang nucleosynthesis predictions and potentially reveal whether the lithium problem extends beyond our local galactic neighborhood. Chapter 13. The Measurement Problem. When does reality decide? Every time you observe something, checking the time on your phone, noticing the color of a sunset, or measuring the temperature in your room, you're participating in one of the deepest mysteries in all of physics. The act of measurement appears to force the quantum world to abandon its fuzzy, probabilistic existence and suddenly snap into the definite, classical reality you experience. Before measurement, quantum systems exist in superposition, simultaneously embodying all possible states according to their wave function. An electron can be spinning up and down at the same time, a photon can be traveling through multiple paths simultaneously, and a radioactive atom can be both decayed and undecayed until someone checks. This isn't a limitation of our knowledge. According to quantum mechanics, the system genuinely exists in all these states at once. But the moment you make a measurement, this superposition instantly collapses into a single, definite outcome. The electron becomes either spin up or spin down, the photon chooses one path, and the atom becomes definitely decayed or definitely intact. This sudden transition from quantum fuzziness to classical definiteness is called wave function collapse, and nobody understands how or why it occurs. The measurement problem becomes even more mysterious when you consider what constitutes a measurement. Does collapse require a conscious observer, or can any interaction with the environment trigger the transition? If a tree falls in a quantum forest with no one around to hear it, does its wave function collapse when it hits the ground? Various interpretations of quantum mechanics offer different answers, each with profound implications for the nature of reality. The Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, suggests that quantum systems remain in superposition until measurement forces them to choose definite values. But this interpretation provides no mechanism for collapse and leaves the boundary between quantum and classical behavior undefined. The many worlds interpretation proposed by Hugh Everett eliminates collapse entirely by suggesting that all possible measurement outcomes occur simultaneously in parallel branches of reality. When you measure an electron spin, the universe splits into multiple versions where every possible result happens. You experience only one outcome because your consciousness becomes correlated with one particular branch. Other interpretations propose that consciousness plays a fundamental role in quantum mechanics. These theories suggest that wave function collapse occurs only when information enters conscious awareness, making observers active participants in creating physical reality rather than passive recipients of pre-existing facts. Recent experiments have pushed the measurement problem into increasingly exotic territory. Quantum interference effects have been demonstrated with molecules containing thousands of atoms, suggesting that superposition can persist in objects approaching macroscopic scales. Other experiments have shown quantum entanglement between systems separated by hundreds of kilometers, indicating that measurement of one system can instantaneously influence the state of its distant partner. The measurement problem intersects with fundamental questions about the nature of information and computation. If quantum systems can exist in superposition until measured, then quantum computers might be able to perform calculations using all possible input states simultaneously. But extracting useful information from such quantum computations requires measurement, which seems to destroy the very superposition that provided the computational advantage. Perhaps most mysteriously, the measurement problem suggests that the act of observation might play a fundamental role in determining physical reality. If wave function collapse requires measurement, then the universe might be constantly creating itself through the accumulation of observational acts performed by conscious beings and measuring devices throughout cosmic history. Chapter 14. The Information Paradox. What happens when black holes evaporate? Black holes represent perhaps the most extreme predictions of general relativity, regions where space-time curvature becomes so severe that nothing, not even light, can escape once it crosses the event horizon. But in the 1970s, Stephen Hawking made a startling discovery that revealed a fundamental conflict between general relativity and quantum mechanics. According to Hawking's calculations, black holes aren't perfectly black. Quantum fluctuations near the event horizon should cause them to emit thermal radiation, slowly evaporating away over enormous timescales. For stellar mass black holes, this evaporation process would take longer than the current age of the universe, but smaller black holes would disappear much more rapidly. The radiation appears to be completely random thermal emission, containing no information about the matter that originally fell into the black hole. This creates what's known as the black hole information paradox. If black holes evaporate completely through Hawking radiation, what happens to the information that was encoded in the matter that formed them? Quantum mechanics demands that information be conserved in all physical processes. When you burn a book, the information in its pages isn't destroyed. It becomes scrambled and distributed among the smoke, ash, and photons produced by the fire. With sufficient knowledge and computational power, you could, in principle, reconstruct the original text from these byproducts. But Hawking radiation appears to violate this principle by destroying information permanently. The paradox has generated decades of theoretical research and debate, with proposed solutions ranging from subtle modifications to Hawking's original calculations to revolutionary changes in our understanding of spacetime itself. Some theories suggest that information is preserved in subtle correlations within the Hawking radiation that become apparent only when the black hole has nearly completely evaporated. Other approaches propose that black holes don't actually destroy information, but instead create shortcuts through space-time that connect the interior to distant regions of the universe. In these models, information that appears to be lost might actually be transmitted to other locations through quantum entanglement or wormhole-like connections. Perhaps most radically, some physicists have suggested that the information paradox reveals fundamental limits to the applicability of general relativity inside black holes. If quantum effects become important near the singularity, they might prevent information destruction through mechanisms we don't yet understand. The paradox has taken on new urgency with recent observations of black hole mergers by gravitational wave detectors. These events provide direct tests of general relativity in the strongest gravitational fields ever observed, but they also create new puzzles about information flow and conservation during black hole interactions. The mystery extends beyond academic physics into fundamental questions about the nature of space, time, and information itself. If black holes can destroy information, it would require abandoning one of the most successful principles in physics. But if information is preserved, it might require accepting that the interior of black holes operates according to laws we haven't yet discovered. Recent theoretical developments have suggested that the information paradox might be resolved through holographic principles, where all the information that appears to fall into a black hole is actually encoded on its two-dimensional surface. This holographic duality could revolutionize our understanding of space-time and gravity, suggesting that three-dimensional reality might emerge from more fundamental two-dimensional information processing. The stakes of resolving this paradox extend far beyond black hole physics. The principles involved, information conservation, the relationship between quantum mechanics and gravity, and the fundamental nature of space-time, underlie our most basic understanding of physical reality. The answer might require a complete revolution in physics comparable to the transitions from classical mechanics to relativity and quantum theory. As gravitational wave astronomy continues to mature and new theoretical tools are developed, we're entering an era where the information paradox might finally be resolved through direct observation and mathematical breakthrough. The answer will determine not just our understanding of black holes, but the fundamental principles that govern information, reality, and existence itself in our strange and wonderful universe. But perhaps the most unsettling aspect of all these cosmic mysteries is this. Each new discovery seems to reveal 10 new puzzles for every question we answer. The universe appears to be constructed from layers of mystery nested within larger mysteries, like cosmic Russian dolls that extend infinitely inward and outward from our current understanding. We stand at a unique moment in the history of human knowledge, equipped with instruments powerful enough to peer into the heart of atoms and across billions of light years of space, yet surrounded by enigmas that challenge our most fundamental assumptions about the nature of existence itself. The cosmos continues to whisper its secrets in languages we're only beginning to learn, through signals we're barely beginning to detect, revealing truths that stretch the boundaries of imagination while remaining tantalizingly beyond our complete comprehension. Chapter 15: The Quantum Tunneling Paradox, when particles break the speed limit. Every second, particles throughout your body are doing something that should be absolutely impossible according to classical physics. They're passing through barriers that should stop them cold, appearing on the other side without ever having enough energy to climb over the wall. This phenomenon, called quantum tunneling, operates in the circuits of your smartphone, powers the fusion reactions inside stars, and enables the radioactive decay that keeps Earth's core molten. But here's where quantum tunneling becomes truly mysterious. Recent experiments suggest that particles might be traveling faster than light during the tunneling process itself. This isn't science fiction speculation. It's a measurable effect that has physicists questioning fundamental assumptions about causality and the nature of space-time. Picture an electron encountering a barrier that's far too high for it to surmount using its available energy. Classical physics predicts the electron should bounce back like a ball hitting a wall, but quantum mechanics reveals that the electron's wave function extends through the barrier, giving it a probability of spontaneously appearing on the other side. The electron doesn't climb over the barrier or burrow through it. It simply materializes on the other side, as if the barrier didn't exist. This quantum teleportation occurs constantly throughout the natural world. The nuclear fusion that powers the sun depends on protons tunneling through the electromagnetic barrier that should prevent them from getting close enough to fuse. Without tunneling, stellar cores would need temperatures millions of times hotter to overcome these barriers through thermal energy alone. The universe would be a cold, dark place where stars never ignited. But measurements of tunneling times have revealed something deeply disturbing. When particles tunnel through barriers, they appear to spend zero time inside the barrier itself. More precisely, experiments show that particles emerge from barriers before they should have had time to traverse them, even at the speed of light. Some measurements suggest effective tunneling speeds that exceed light speed by orders of magnitude. This apparent faster-than-light transmission creates a causality paradox. If information can be transmitted instantaneously through quantum tunneling, it might be possible to send signals backward in time, creating grandfather paradox scenarios where effects precede their causes. Yet despite decades of increasingly sophisticated experiments, no one has managed to use tunneling to transmit usable information faster than light. The resolution might lie in the distinction between phase velocity and group velocity in quantum wave packets. While individual wave components might propagate faster than light during tunneling, the overall information content travels at subluminal speeds. But this explanation raises new mysteries about the nature of information itself and how quantum systems encode and transmit data. Recent experiments have pushed tunneling into macroscopic regimes, demonstrating quantum tunneling effects in systems containing thousands of atoms. These measurements suggest that the boundary between quantum and classical behavior might be far more complex than previously imagined, with macroscopic objects potentially exhibiting quantum tunneling under specific conditions. The mystery deepens when we consider tunneling's relationship to the measurement problem in quantum mechanics. The act of measuring whether a particle has tunneled through a barrier appears to affect the tunneling probability itself, suggesting that observation plays a fundamental role in determining quantum outcomes. This observer effect in tunneling experiments provides another window into the deep connections between consciousness, measurement, and quantum reality. Chapter 16. The Axis of Evil. A universe that shouldn't have direction. The cosmic microwave background radiation should be perfectly uniform in all directions, reflecting the isotropic nature of space itself. After all, if the universe began with a big bang and expanded uniformly in all directions, there should be no preferred axis or orientation in the cosmos. Yet careful analysis of this ancient light has revealed a disturbing pattern that cosmologists have dubbed the Axis of Evil. This ominous name refers to an unexpected alignment in the temperature fluctuations of the cosmic microwave background. Instead of being randomly distributed across the sky, the largest scale temperature variations show a mysterious preference for a particular direction in space. The quadrupole and octupole moments of the radiation pattern align along an axis that coincidentally points toward the constellation Virgo and lies roughly in the plane of our solar system. The probability of this alignment occurring by chance is less than 1%, suggesting either extraordinary cosmic coincidence or fundamental problems with our understanding of cosmological structure. The pattern violates the cosmological principle, which assumes that the universe looks the same in all directions on large scales. If the axis of evil represents genuine cosmological structure, it would require revolutionary changes to our models of cosmic evolution. Various explanations have been proposed, each more exotic than the last. Some theories suggest that the alignment results from interactions between our universe and neighbouring bubble universes in a vast multiverse ensemble. These cosmic collisions during the inflationary epoch could have imprinted preferred directions into the cosmic microwave background that persist to this day. Other models propose that the axis of evil reflects the influence of extra dimensions of space that we cannot directly perceive. If our three-dimensional universe exists as a membrane embedded in higher dimensional space, the geometry of these extra dimensions might create observable anisotropies in the cosmic microwave background radiation. Perhaps most unsettling is the possibility that the alignment is somehow related to our local environment within the solar system or galaxy. While this seems impossible, given the cosmic scales involved, some researchers have suggested that previously unknown systematic effects in our measurement techniques might create artificial patterns in the data. The mystery has intensified with more recent observations from advanced cosmic microwave background missions. The Planck satellite, with unprecedented sensitivity and resolution, has confirmed the reality of the axis of evil while revealing additional anomalous patterns that seem to correlate with structures in our local cosmic neighborhood. These discoveries challenge the fundamental assumption of cosmological isotropy that underlies modern cosmology. If the universe possesses genuine, large-scale anisotropies, it would require rethinking everything from dark energy models to the mechanisms of cosmic inflation. The implications extend beyond academic cosmology into philosophical questions about the nature of space, time, and our place within cosmic architecture. Chapter 17: The Pioneer Anomaly, Spacecraft that Refused to Obey Physics. In the outer reaches of our solar system, two robotic explorers launched in the 1970s began exhibiting behavior that defied every prediction of celestial mechanics. Pioneer 10 and Pioneer 11, humanity's first emissaries to the outer planets, were experiencing a mysterious force that was slowing them down in ways that couldn't be explained by known physics. The anomaly was subtle, but undeniable. Both spacecraft were decelerating at a rate of approximately 8.74 times 10 to the power of -10 meters per second squared, a tiny acceleration directed toward the Sun that accumulated over decades of flight. This deceleration was far too large to be explained by solar radiation pressure, interplanetary magnetic fields, or gravitational effects from known bodies in the solar system. What made the Pioneer anomaly particularly mysterious was its consistency. The anomalous acceleration remained constant over enormous distances, from the orbit of Saturn to beyond the orbit of Neptune. If some unknown gravitational effect was responsible, it would have to operate according to laws different from Einstein's general relativity or Newton's inverse square law. The discovery sent shockwaves through the physics community because it suggested either systematic errors in our most precise spacecraft navigation techniques or the existence of new physics operating on solar system scales. Some theorists proposed modifications to gravitational theory that would produce the observed effects, while others suggested the influence of dark matter or extra-dimensional forces. For decades, the Pioneer anomaly remained one of the most puzzling, unsolved problems in experimental physics. The effect was too large and too consistent to ignore, yet no conventional explanation could account for the observations. The spacecraft had become unintentional laboratories for testing fundamental physics in the weak field, long-distance regime where deviations from general relativity might become apparent. The mystery was eventually solved through painstaking analysis of thermal radiation from the spacecraft themselves. The radioisotope thermoelectric generators that powered the Pioneers emitted waste heat preferentially in directions that created a tiny but persistent rocket effect. When this thermal recoil force was carefully modelled, it precisely matched the observed anomalous acceleration. While the resolution of the Pioneer anomaly eliminated one potential window into new physics, it demonstrated the extraordinary precision required for testing gravitational theory using spacecraft. The investigation also revealed how difficult it can be to account for all possible systematic effects when pushing the boundaries of measurement precision. The Pioneer experience has informed the design of subsequent missions intended to test fundamental physics. Projects like the proposed STEP satellite and the ongoing analysis of data from the Cassini mission continue searching for deviations from general relativity that might reveal new aspects of gravitational behavior. But the Pioneer anomaly serves as a reminder that even our most successful theories might contain surprises. The fact that a thermal effect could masquerade as new physics for decades illustrates how much we still don't understand about the complex interactions between matter, energy, and space-time in the cosmos. Chapter 18: The Wow Signal, a message we can't decode. On August 15, 1977, at 11:16 p.m. Eastern Time, the Big Ear radio telescope in Ohio detected something that shouldn't exist according to our understanding of natural astronomical phenomena. For exactly 72 seconds, the telescope recorded a powerful radio signal that appeared to originate from the constellation Sagittarius. The signal was so unusual that astronomer Jerry Amon circled the data printout and wrote "Wow" in the margin, giving the detection its enduring name. The WOW signal exhibited characteristics that made it unlike any known natural radio source. It was transmitted at a frequency of 1420 MHz, the exact wavelength at which hydrogen atoms emit radiation when they flip their electron spin states. This frequency is considered so fundamental to cosmic chemistry that many scientists have proposed it as a logical choice for interstellar communication attempts. The signal's intensity was extraordinary, roughly 30 times stronger than the typical background noise level. But perhaps most intriguingly, it showed the precise frequency drift that would be expected from a source located beyond our solar system. As Earth rotated during the observation period, the Doppler shift caused by our planet's motion created exactly the pattern that would be produced by a distant, stationary transmitter. What made the WOW signal truly mysterious was its brevity and the fact that it was never detected again. Despite decades of follow-up observations using increasingly sophisticated equipment, no trace of the signal has been found. The source region has been monitored continuously by radio telescopes around the world. But whatever created that powerful 72-second transmission has remained completely silent. The characteristics of the WOW signal match theoretical predictions for artificial radio transmissions better than any natural phenomenon we understand. Astronomical radio sources typically emit across broad frequency ranges and maintain relatively constant intensity over time. The WOW signal, in contrast, was precisely tuned to a single frequency and appeared exactly once before vanishing completely. Various natural explanations have been proposed over the decades. Some astronomers suggest the signal resulted from reflection of Earth-based transmissions, off-space debris, or atmospheric phenomena. Others propose exotic astrophysical processes involving neutron stars, black holes, or interstellar masses that might produce brief, powerful radio bursts. Recent analysis has focused on the possibility that the signal originated from hydrogen clouds in interstellar space that were excited by some unknown energy source. Computer models suggest that certain configurations of cosmic masers might amplify radio emissions at the hydrogen frequency, creating brief but powerful signals that could explain the WOW detection. But none of these explanations fully account for all the observed characteristics. The signal's precise frequency, its duration, its intensity, and its failure to repeat create a combination of properties that remains difficult to explain through conventional astrophysics. The search for similar signals continues through projects like the Breakthrough Listen initiative, which monitors millions of stars for signs of artificial radio transmissions. These modern SETI programs use techniques far more sensitive than those available in 1977, yet they have found no clear repetitions of the WOW signal phenomenon. The mystery has taken on additional significance with the recent discovery of fast radio bursts, powerful radio signals from distant galaxies that appear briefly and often don't repeat. While FRBs operate at different frequencies and originate from much greater distances, they demonstrate that the universe can produce radio phenomena that exceed our current understanding. Whether the WOW signal represents a glimpse of extraterrestrial intelligence, an unknown natural phenomenon, or simply an instrumental artifact that we'll never fully understand, it continues to embody the tantalizing possibility that we might not be alone in our cosmic journey of discovery and wonder. Chapter 19. The Fine Structure Constant, Nature's Most Mysterious Number. Buried deep within the mathematical foundations of physics lies a number so fundamental and mysterious that it has puzzled scientists for over a century. The fine structure constant typically denoted by the Greek letter alpha, has a value of approximately 1/137th. This dimensionless number determines the strength of electromagnetic interactions and influences virtually every aspect of atomic structure and chemical behavior. What makes the fine structure constant so mysterious isn't just its precise value, but the fact that we have absolutely no theoretical understanding of why it has this value rather than any other. Unlike other fundamental constants that can be defined arbitrarily through our choice of units, alpha is a pure number that would have the same value regardless of whether you measured it in meters and seconds or light years and millennia. The constant appears in equations throughout physics, determining everything from the spacing of atomic energy levels to the transparency of matter to electromagnetic radiation. If alpha were significantly different, atoms couldn't exist as stable structures, stars couldn't shine through nuclear fusion, and the chemistry necessary for life would be impossible. Richard Feynman, one of the greatest physicists of the 20th century, called the fine structure constant one of the greatest damn mysteries of physics, and suggested that all good theoretical physicists should worry about its value. He noted that the number appears to be completely arbitrary from a theoretical standpoint, yet its precise value determines whether our universe can support complex structures and life. The mystery deepens when you consider that alpha might not actually be constant. Astronomical observations of distant quasars have suggested that the fine structure constant might have been slightly different billions of years ago, changing slowly over cosmic time. If confirmed, this would revolutionize our understanding of fundamental physics and suggest that what we consider immutable laws of nature might actually evolve. Different research groups have reported conflicting results about temporal variation in alpha. Some studies of quasar absorption lines suggest the constant was smaller in the early universe, while others find no evidence for change. The discrepancies might result from systematic measurement errors, or they might indicate that alpha varies differently in different regions of space. The possibility of spatial variation in fundamental constants is even more radical. If alpha has different values in different parts of the universe, it would create a cosmic landscape where the laws of physics themselves change from place to place. This could explain the apparent fine-tuning of our local cosmic environment, while suggesting that most regions of space are hostile to complex structure formation. Theoretical attempts to explain alpha's value have invoked everything from anthropic selection principles to extra dimensions and string theory. Some models suggest that alpha is determined by the geometry of hidden spatial dimensions that we cannot directly perceive. Others propose that its value results from dynamic processes in the early universe that we don't yet understand. Recent experiments using atomic clocks and precision spectroscopy have placed increasingly stringent limits on any possible variation in alpha over human timescales. These measurements have reached precisions where changes of a few parts in 10 to the power of 17 per year would be detectable, yet no definitive variation has been observed. The search for alpha variation has implications far beyond fundamental physics. If the fine structure constant changes over time or space, it could affect the interpretation of astronomical observations, the reliability of atomic clocks used for GPS navigation, and even the long-term stability of matter itself. Perhaps most intriguingly, some theories suggest that consciousness and intelligence might play a role in determining the values of fundamental constants. If observer selection effects influence the physical laws we observe, then alpha's value might reflect not just blind physical processes, but the requirement that the universe be capable of supporting observers capable of measuring it. Chapter 20. The Moon's Impossible Origin, our satellite that shouldn't exist. Every night you look up at an object that represents one of the most perplexing puzzles in planetary science. Earth's moon is far too large, too close, and too compositionally similar to our planet to be explained by conventional theories of satellite formation. In fact, according to our best understanding of planetary dynamics, the moon shouldn't exist at all. The mystery begins with the moon's extraordinary size relative to Earth. Most planets in our solar system have satellites that are tiny compared to their parent worlds. Jupiter's largest moon, Ganymede, represents only 0.008% of Jupiter's mass, but our moon constitutes 1.2% of Earth's mass, making the Earth-Moon system more like a double planet than a traditional planet-satellite pair. This size relationship creates dynamical problems that have puzzled astronomers for centuries. If the moon formed from the same primordial disk of material that created Earth, it should have a very different composition, enriched in light elements that would have remained in the outer regions of the disk. Instead, the moon's composition is remarkably similar to Earth's mantle, suggesting a common origin that conventional formation models cannot explain. The moon's orbital characteristics add another layer to the mystery. It orbits in the same plane as Earth's equator and rotates synchronously, always showing the same face toward our planet. This configuration requires specific initial conditions that seem improbable if the moon formed through capture of a wandering asteroid or gradual accretion of orbital debris. Perhaps most puzzling is the moon's internal structure. Despite its relatively small size, the moon shows evidence of having been completely molten early in its history, creating a global magma ocean that differentiated into the layered structure we observe today. Generating enough heat to melt an entire moon-sized body requires energy sources that remain mysterious. The leading explanation for these anomalies involves a catastrophic collision between the early Earth and a Mars-sized planetary embryo called Theia. This giant impact hypothesis proposes that the collision vaporized portions of both bodies, creating a disk of hot debris around Earth that eventually coalesced into the moon. The violence of this impact would explain the moon's unusual composition, its large size, and the energy required for global melting. Computer simulations of giant impacts can reproduce many observed features of the Earth-Moon system, but they also create new puzzles. The collision would have imparted enormous angular momentum to the Earth-Moon system, causing our planet to rotate much faster than observed. Some mechanism must have subsequently removed this excess angular momentum through interactions we don't fully understand. Recent analysis of lunar samples has revealed isotopic compositions that are virtually identical to Earth's mantle, suggesting an even more intimate connection between the two bodies than the original giant impact models predicted. This isotopic similarity requires fine-tuning the collision parameters in ways that seem improbable given the chaotic nature of early planetary formation. Alternative theories continue to challenge the giant impact hypothesis. Some researchers propose that the moon formed through gradual accretion of material captured from Earth's extended atmosphere, while others suggest multiple smaller impacts rather than a single catastrophic collision. Each model faces its own set of observational challenges and requires specific initial conditions that seem unlikely. The moon's existence has profound implications for life on Earth. Its gravitational influence stabilizes Earth's rotational axis, preventing chaotic climate variations that would make complex life evolution extremely difficult. The tides created by lunar gravity might have played crucial roles in the transition of life from ocean to land. Without the moon, Earth might be a very different and possibly lifeless world. As we continue to study lunar samples and develop more sophisticated models of planetary formation, the moon's origin remains one of the most compelling unsolved puzzles in our cosmic neighborhood. The fact that our closest celestial neighbor harbors such deep mysteries reminds us that even the most familiar objects in our universe can challenge our understanding in unexpected ways. Chapter 21: The Ultraviolet Catastrophe. When classical physics breaks down. At the dawn of the 20th century, physicists faced a crisis that would ultimately revolutionize our understanding of reality itself. The problem seemed simple enough. Predict the color of light emitted by a perfectly absorbing and radiating object, what physicists call a black body, when heated to different temperatures. Classical physics provided clear equations for solving this problem. The energy of electromagnetic radiation should be distributed smoothly across all possible frequencies, with higher energy radiation carrying proportionally more energy. When physicists applied these classical theories to calculate the spectrum of blackbody radiation, they obtained a result so absurd it threatened the foundations of physics itself. According to classical predictions, any heated object should emit infinite amounts of energy in the ultraviolet portion of the electromagnetic spectrum. This meant that every warm object, from your coffee cup to your own body, should be blazing with deadly ultraviolet radiation, intense enough to kill you instantly. The theoretical prediction was so far from observed reality that physicists dubbed it the ultraviolet catastrophe. The resolution came from an unlikely source: Max Planck's desperate attempt to match theory with experiment by making what he thought was a purely mathematical trick. In 1900, Planck proposed that electromagnetic energy could only be emitted or absorbed in discrete packets, or quanta, rather than in the continuous amounts that classical physics assumed. Planck's quantum hypothesis solved the ultraviolet catastrophe by showing that high-frequency radiation requires enormous amounts of energy per quantum. At normal temperatures, there isn't enough thermal energy available to excite these high-frequency modes, naturally cutting off the catastrophic ultraviolet emission that classical theory predicted. But Planck's solution came at an enormous cost. It required abandoning the classical assumption that energy flows smoothly and continuously. Instead, energy appeared to be granular, chunky, quantized in ways that violated every intuition about how the physical world should behave. This was the birth of quantum mechanics, though neither Planck nor his contemporaries realized the revolutionary implications of his mathematical fix. The quantum solution to the ultraviolet catastrophe revealed that our everyday experience of smooth, continuous phenomena emerges from underlying, discrete, quantized processes. The seemingly solid matter around you consists of atoms that can only exist in specific energy states, absorbing and emitting light in precise amounts determined by quantum mechanical rules. This discreteness extends far beyond electromagnetic radiation into the fundamental structure of space, time, and matter itself. Quantum field theory suggests that even the vacuum of empty space consists of discrete quantum fluctuations that pop in and out of existence on timescales so brief they escape direct detection. The ultraviolet catastrophe also foreshadowed other infinities that plague theoretical physics. When physicists try to calculate the energy density of quantum vacuum fluctuations, they encounter the same type of divergent integrals that created the original blackbody radiation problem. These infinities suggest fundamental limits to our current theoretical frameworks and the need for new principles that can tame the mathematical monsters lurking in our equations. Modern physics continues to grapple with similar catastrophes that arise when classical intuitions are pushed to their limits. The hierarchy problem in particle physics involves fine-tuning requirements that seem to require miraculous cancellations between different physical effects. The cosmological constant problem represents another ultraviolet-type catastrophe, where quantum predictions exceed observations by factors that dwarf even the original blackbody radiation discrepancy. Each time physicists encounter these mathematical infinities, they signal the need for revolutionary new concepts that transcend our current understanding. The ultraviolet catastrophe taught us that energy is quantized. Future catastrophes might reveal equally fundamental aspects of reality that we haven't yet imagined. The legacy of the ultraviolet catastrophe reminds us that some of the most profound discoveries in physics emerge from seemingly technical problems with our theoretical predictions. When our best mathematical models give absurd results, nature is usually trying to teach us something fundamental about the hidden principles that govern reality itself. Chapter 22. The Stellar Impossible, Stars that Break Their Own Rules. Throughout the cosmos, astronomers are discovering stars that violate everything we thought we understood about stellar evolution. These cosmic rebels are burning too brightly, living too long, or exhibiting chemical compositions that contradict decades of carefully constructed theoretical models. Consider the mystery of blue stragglers, stars that appear far younger than they should be given their location in ancient star clusters. These stellar time travelers glow with the blue-white light characteristic of hot, massive young stars, yet they exist in globular clusters that formed over 12 billion years ago. Any truly massive star should have exhausted its nuclear fuel and died long before the present day. The existence of blue stragglers suggests that stellar aging isn't as straightforward as we once believed. These stars might have found ways to rejuvenate themselves through collisions with companions, mass transfer from nearby stars, or exotic nuclear processes that extend their lifetimes far beyond theoretical predictions. Each explanation raises new questions about stellar dynamics and nuclear physics in extreme environments. Even more puzzling are the Thorne-Zhitkov objects, hypothetical stars that consist of a neutron star core surrounded by a normal stellar envelope. The extreme gravitational field of the central neutron star should create nuclear reaction chains impossible in ordinary stars, producing elements that serve as smoking guns for this exotic stellar architecture. Recent observations have identified candidate objects with the predicted chemical signatures, but their very existence challenges our understanding of stellar collision dynamics and stability. Magnetars represent another category of impossible stars, neutron stars with magnetic fields so intense they approach the limits of what quantum mechanics allows. These objects possess magnetic fields trillions of times stronger than Earth's, powerful enough to strip electrons from atoms and bend spacetime itself. The energy stored in their magnetic fields exceeds the total energy output of our Sun over millions of years. Yet we have no complete theory for how such extreme magnetization develops or maintains itself. The recent discovery of kilonovae has revealed that neutron star mergers create conditions so extreme they forge gold, platinum, and other heavy elements through rapid neutron capture processes. These cosmic foundries operate under physical conditions that push nuclear physics into uncharted territory, creating elements through reaction chains that laboratory experiments can barely begin to explore. Perhaps most mysteriously, some stars appear to be missing entirely. Theoretical models predict that certain types of massive stars should undergo specific types of collapse or explosion, yet searches for the predicted remnants come up empty. These failed supernovae might be collapsing directly into black holes without the explosive fireworks that normally accompany stellar death, leaving behind gaps in our observations that hint at hidden pathways in stellar evolution. Population 3, stars, the first generation of stars that formed in the primordial universe, remain entirely hypothetical despite decades of searching. These stars should have been massive, short-lived, and composed entirely of hydrogen and helium, since no heavier elements existed when they formed. Their explosions should have seeded space with the first heavy elements, making all subsequent chemistry possible. Yet we've never directly observed a population 3 star, raising questions about whether our models of early stellar formation are fundamentally correct. Some of the most ancient stars in our galaxy show chemical compositions that seem impossible according to standard nucleosynthesis models. They contain elements that shouldn't exist given their age and environment, suggesting either that our understanding of stellar nuclear processes is incomplete, or that these stars have experienced encounters with exotic phenomena we haven't yet identified. Chapter 23. The Great Attractor. Something massive is pulling our galaxy. Hidden behind the dusty plain of our own Milky Way galaxy lurks something so massive it's dragging us and thousands of neighbouring galaxies toward it at over 600 kilometers per second. This gravitational monster, dubbed the Great Attractor, represents one of the most perplexing large-scale structures in the observable universe. The discovery began in the 1970s when astronomers noticed something disturbing about the cosmic microwave background radiation. After accounting for our motion around the sun's motion around the galaxy, and the galaxy's motion through space, there remained an unexplained component of our velocity that suggested we're being pulled toward the constellation Hydra Centaurus by some unseen gravitational influence. What makes the Great Attractor so mysterious is its location in the zone of avoidance, a region of sky so obscured by dust and stars from our own galaxy that we can barely see through it. It's like trying to study a distant mountain range while standing in a dense forest. The very thing we most need to observe is hidden behind a cosmic curtain of intervening matter. Initial estimates suggested the Great Attractor contained the mass equivalent of tens of thousands of galaxies concentrated in a region roughly 150 million light-years away. But as observations improved and the dust began to clear, astronomers realized they were dealing with something far more complex than a simple massive galaxy cluster. The Great Attractor appears to be part of an even larger structure called the Laniakea supercluster, a vast web of galaxies, dark matter, and empty space that spans over 500 million light-years. Our own Milky Way galaxy sits on the outskirts of this cosmic metropolis, being drawn inexorably toward its gravitational center along with thousands of other galactic citizens. But the mystery deepens when we try to account for all the mass needed to create such powerful gravitational attraction, even including dark matter estimates. The visible and inferred mass in the Great Attractor region seems insufficient to explain the observed velocities of galaxies streaming toward it. Either our understanding of dark matter distribution is fundamentally wrong, or there's something even more exotic hiding in this cosmic shadow zone. Recent surveys using infrared telescopes that can peer through galactic dust have begun to reveal the true nature of what's pulling us through space. The region contains several massive galaxy clusters, walls of galaxies, and vast filamentary structures that form part of the cosmic web. But rather than a single Great Attractor, we appear to be witnessing the gravitational influence of multiple massive structures working in concert. Even more intriguingly, the Great Attractor itself appears to be falling toward an even larger gravitational influence called the Shapley supercluster, located roughly 650 million light-years away. This suggests a hierarchy of cosmic structures, each pulling on the next in a gravitational cascade that extends across significant fractions of the observable universe. The implications are staggering. If massive structures can influence galactic motion across such enormous distances, it suggests that the universe's large-scale architecture is even more interconnected than we realized. The fate of our galaxy might be determined not by local gravitational influences, but by the collective gravitational pull of cosmic structures so vast they dwarf our current understanding of cosmic organization. This cosmic dance also raises questions about the ultimate fate of galaxy clusters and superclusters. Will the Great Attractor eventually pull in all the surrounding galaxies to form an even more massive structure? Or will the accelerating expansion of space, driven by dark energy, overcome these gravitational attractions, leaving isolated islands of matter separated by ever-expanding voids? Chapter 24. the impossible elements, matter that shouldn't exist. Deep in the hearts of the most massive stars, and in the violent explosions that end their lives, nature creates elements so exotic they challenge our understanding of nuclear physics itself. These super-heavy elements exist at the very limits of atomic stability, in realms where the fundamental forces that hold matter together are stretched to their breaking points. The periodic table, as we know it, contains 118 confirmed elements, but theoretical calculations suggest that much heavier elements might be possible under the right conditions. These hypothetical super-heavy elements would possess nuclear properties unlike anything in our terrestrial experience, potentially exhibiting forms of radioactivity and nuclear behavior that we've never observed. At the frontier of nuclear physics lies the island of stability, a theoretical region where super-heavy nuclei might exist for minutes, hours, or even years, rather than the microseconds typical of most artificial elements. These stable super-heavy elements could possess chemical and physical properties so unusual they would constitute entirely new categories of matter, with applications we can barely imagine. The challenge in creating super-heavy elements lies in overcoming the electromagnetic repulsion between the enormous number of protons packed into their nuclei. As atomic nuclei get larger, the electromagnetic force trying to blow them apart grows stronger, while the strong nuclear force holding them together reaches its limits. Only the most extreme conditions can force enough protons and neutrons together to create these exotic atomic architectures. Recent experiments at particle accelerators have pushed the boundaries of element creation, synthesizing atoms with over 100 protons in their nuclei. These super-heavy elements exist for mere fractions of a second before decaying into lighter elements, but their brief existence provides windows into nuclear physics operating under conditions that don't occur naturally anywhere in the known universe. What makes super-heavy elements particularly mysterious is their potential abundance in certain cosmic environments. The neutron-rich conditions created during neutron star mergers might naturally synthesize elements far heavier than anything we can create in terrestrial laboratories. These cosmic foundries operate with neutron fluxes so intense they could overcome the stability barriers that limit artificial element production. Some theoretical models suggest that super-heavy elements created in neutron star mergers might be stable enough to survive the explosive dispersal into interstellar space, potentially seeding the universe with forms of matter that we've never detected. These exotic elements could possess nuclear properties that make them essentially invisible to conventional detection methods, while still influencing cosmic evolution in subtle ways. The search for super-heavy elements in space focuses on identifying their unique decay signatures in cosmic ray particles and meteorites. If stable super-heavy elements exist naturally, they might occasionally reach Earth as components of interstellar dust or rare meteoritic inclusions. Detecting even a few atoms would revolutionize our understanding of nuclear physics and cosmic element formation. Perhaps most intriguingly, some super-heavy elements might exhibit properties that border on the supernatural. Theoretical calculations suggest that certain super-heavy isotopes could undergo decay processes that release enormous amounts of energy per atom, potentially serving as the ultimate energy storage medium. Others might possess magnetic or electrical properties, unlike anything in the conventional periodic table. The implications extend beyond nuclear physics into fundamental questions about the nature of matter itself. If stable super-heavy elements exist, they could represent forms of atomic matter that operate according to different rules than the familiar elements that make up our bodies and our world. They might possess quantum mechanical properties that blur the boundaries between atomic and nuclear physics. Chapter 25. The Quantum Zeno Effect when watching changes everything. In the quantum world, the simple act of observation doesn't just reveal reality, it fundamentally changes what's possible. This profound connection between measurement and physical behavior reaches its most extreme expression in a phenomenon so counterintuitive it's named after a philosopher's paradox, the quantum Zeno effect. The effect takes its name from Zeno of Elea, who argued that motion is impossible because any moving object must pass through an infinite number of intermediate positions, requiring infinite time. In quantum mechanics, continuous observation of a decaying particle can indeed freeze it in its initial state, preventing the decay that should occur according to all physical laws. Picture a radioactive nucleus that has a 50% chance of decaying within 1 hour. According to quantum mechanics, the act of measuring whether it has decayed determines the outcome of that measurement. But here's where things become truly bizarre. If you check on the nucleus every few seconds, you can actually prevent it from decaying at all. The continuous measurements collapse the quantum superposition so frequently that the system never has time to evolve into its decayed state. This isn't a thought experiment or theoretical curiosity. Laboratory demonstrations of the quantum Zeno effect have successfully prevented atomic decay, halted chemical reactions, and frozen quantum systems in specific states through the power of observation alone. The effect reveals that measurement in quantum mechanics isn't a passive process of gathering information, but an active intervention that shapes physical reality. The implications extend far beyond nuclear physics into fundamental questions about the nature of time, causality, and the role of consciousness in physical processes. If observation can prevent natural processes from occurring, it suggests that the boundary between observer and observed is far more complex than classical physics assumed. Recent experiments have pushed the quantum Zeno effect into macroscopic regimes, demonstrating that observation can influence the behavior of systems containing thousands of atoms. These results suggest that the strange rules of quantum measurement might apply to much larger scales than previously thought, potentially affecting biological processes and technological systems in ways we're only beginning to understand. The effect also raises profound questions about the nature of time itself in quantum systems. If continuous observation can freeze a system in its initial state, it suggests that the flow of time might be dependent on measurement and observation rather than representing an absolute feature of physical reality. Some researchers have proposed that the quantum Zeno effect might play a role in biological systems, where quantum coherence effects could be stabilized through environmental interactions that act like continuous measurements. This could help explain how delicate quantum processes survive in the warm, noisy environments of living cells. The quantum Zeno effect represents one of the clearest demonstrations that reality, at its most fundamental level, operates according to principles that violate our everyday intuitions about causality, time, and the relationship between mind and matter. It suggests that consciousness and observation might play fundamental roles in determining the structure of physical reality itself. Chapter 26. The Cosmological Coincidences, a Universe Fine-Tuned for Existence. The universe appears to be balanced on a knife's edge between existence and oblivion, with fundamental constants and physical laws calibrated to a precision that seems almost impossibly unlikely. Change any of these parameters by tiny amounts, and stars wouldn't shine, atoms couldn't exist, and the cosmos would be nothing but empty space, or collapsed into black holes. Consider the strength of the strong nuclear force that binds protons and neutrons together in atomic nuclei. If this force were just 2% weaker, deuterium couldn't form, and stellar nucleosynthesis would be impossible. There would be no elements heavier than hydrogen in the universe. If the strong force were 2% stronger, hydrogen would be unstable, and all protons would have fused into heavier elements during the Big Bang, leaving no fuel for long-lived stars. The fine structure constant that determines electromagnetic interactions is equally critical. If its value were significantly different, electrons wouldn't bind to atomic nuclei at the right distances to allow complex chemistry. Water molecules couldn't form, carbon bonds would be unstable, and the intricate molecular machinery of life would be impossible. Even more remarkable is the cosmological constant that drives the accelerating expansion of space. This dark energy has a value that's roughly 120 orders of magnitude smaller than theoretical predictions from quantum mechanics suggest it should be. If dark energy were much stronger, galaxies would never have formed because space would expand too rapidly for matter to clump together. If it were much weaker or negative, the universe would have collapsed back on itself long before stars could evolve. The ratio of matter to antimatter in the early universe provides another example of apparent fine-tuning. The tiny excess of matter over antimatter, roughly 1 part in a billion, determined that something rather than nothing would survive the primordial annihilation. This precise imbalance seems arbitrary from a theoretical standpoint, yet it was essential for the existence of all structure in the cosmos. The masses of fundamental particles show similar signs of precise calibration. The mass difference between protons and neutrons is just small enough to allow both particles to exist in atomic nuclei, but large enough to make free neutrons unstable. If this mass difference were slightly different, either all matter would be neutrons making chemistry impossible, or all matter would be protons, preventing the formation of complex nuclei. These coincidences extend to the large-scale structure of space-time itself. The universe appears to be geometrically flat to extraordinary precision. Its density is within 1% of the critical density that separates eternal expansion from eventual collapse. This flatness seems to require initial conditions fine-tuned to better than 1 part in 10 to the power of 60, a level of precision that challenges our understanding of how the universe could have achieved such perfect balance. Various explanations have been proposed for this apparent fine-tuning. The anthropic principle suggests that we observe these special values because we couldn't exist in universes with different parameters. This explanation requires accepting the existence of multiple universes with varying constants, where conscious observers naturally find themselves in the rare realities compatible with their existence. Alternative theories propose that the fundamental constants aren't actually constant but evolved to their current values through physical processes we don't yet understand. Some models suggest that universes undergo natural selection, with constants evolving toward values that maximize the production of complexity and structure. Perhaps most radically, some researchers have suggested that consciousness itself plays a role in determining physical constants through quantum mechanical observer effects operating on cosmic scales. If the act of observation influences physical reality, then the existence of conscious observers might literally tune the universe to values compatible with their continued existence. Tonight, we've journeyed through the deepest mysteries that challenge everything we thought we understood about existence itself. We've explored the invisible scaffolding of dark matter and dark energy that comprises 95% of everything that exists, yet remains completely undetectable to our instruments. We've listened to the cosmic screams of fast radio bursts echoing across billions of light years, carrying messages we cannot decode from sources we cannot identify. We've confronted the fundamental question of why anything exists at all, discovering that our universe survived a primordial annihilation that should have left nothing but empty space and photons. We've grappled with the great silence of the cosmos, where despite billions of potentially habitable worlds, we find ourselves alone in an eerily quiet galaxy. We've peered into impossible galaxies that formed when the universe was barely an infant, yet shine with the complexity of ancient civilizations. And we've stared into the cosmic voids, vast regions of emptiness so profound they challenge our understanding of how matter can organize itself across the universe. Each mystery we've encountered tonight reveals the same humbling truth. We are living in a cosmos far stranger than our ancestors could have imagined. governed by principles that stretch the boundaries of human comprehension. From quantum consciousness to super-heavy elements, from time's arrow to the vacuum catastrophe, every phenomenon we've explored suggests that reality itself operates according to rules we're only beginning to glimpse. But perhaps the most remarkable discovery of all is this. In a universe filled with inexplicable phenomena, impossible structures, and cosmic mysteries that dwarf human understanding, consciousness somehow emerged from ordinary matter and learned to contemplate its own existence. You are stardust that became self-aware, quantum fluctuations that achieved the ability to wonder about quantum mechanics, cosmic evolution that developed the capacity to study cosmology. The mysteries continue to unfold around us every moment, in laboratories pushing the boundaries of the possible, and in telescopes revealing new impossibilities among the stars. Each question we answer seems to reveal 10 new enigmas. Each breakthrough opens doors to territories we never knew existed. We stand at the threshold of discoveries that could transform our understanding of reality itself. Until we meet again on another journey into the cosmic unknown, keep looking up, keep questioning everything you think you know about the universe, and remember that in a cosmos filled with mysteries beyond imagination, the greatest mystery might be consciousness itself, the very awareness that allows you to contemplate these profound questions about existence, reality, and our place in the vast, strange, and utterly magnificent universe we call home.